This is part 22, and I finished this part yesterday, so we're on this one. Exponents, radicals, and scientific notation. Oh shit, that's a lot of videos. Let's go. Exponents. Exponentiation warm-up.
Hi, Sal.
Hey, Britt.
Oh, holy shit.
How are you?
Good. Looks like we have
Cool.
a game going
Is
on
this
here.
Wisconsin?
Not a game, yeah. Kind of a challenge question for you. What I did is I put 1 grain of rice in the first square.
That's right.
There's 64 squares on the board.
Yep.
And at each consecutive
Am I
square,
really recording? 40 seconds in. Okay.
I doubled the amount of rice.
That's right.
There's 64 squares on the board.
Yep.
And at each consecutive square, I doubled the amount of rice.
Wow.
How much rice do you think would be on this square?
On that square. So let me think about it a little bit. Actually, I'm going to take some. So here you have 1.
2 to the
We
like.
multiply that
I
times
know what
2. So
power.
this is going to be 2 times 2. No, 2 times 1. What am I doing? Now this is 2 times that one. So this is 2 times 2. Now this is 2 times that. So this is, okay, we're starting to take a lot of 2's here and multiplying them together. So this is 2 times 2. I'm trying to write sideways. Times
This
2.
2 to the second
So
power.
this one is going to be 5 2's multiplied together. This is going to be 6 2's multiplied together. This is going to be 7 2's multiplied together. 8 2's multiplied together. So 9 2's, 10, 11, 12, 13. So all of this stuff multiplied together. 8,192 grains of rice is what we should see right over here.
And you know, I had fun last night. I was up late, but there you go.
Did you really count out 8,192 grains of rice?
More or less.
Okay, let's just say you did.
What if we just went, 4 steps ahead, and how much rice would be here?
4 steps ahead, so we're going to multiply by 2, then multiply by 2 again, then multiply by 2 again, then multiply by 2 again. So it's this number times, let's see, 2 times 2 is 4, times 2 is 8, times 2 is 16. So it's going to get us like 120, like 130,000 or around there.
131,672.
You got a lot of time last night. We're not even halfway across the board yet.
We're not.
I mean, this is a lot of, that's a lot of rice there. That you could throw a party.
What about the last square? This is 63 steps.
We're gonna take 2 times 2, and we're gonna do 63 of those. So this is going to be a huge number, and actually it would be neat if there was a notation for that.
I didn't count this one out, but it is the size of Mount Everest, the pile of rice, and it would feed 485 trillion people.
But I have one question. I mean, this was a little bit of a pain for me to write all of these 2's.
So is this.
If I were the mathematical community, I would want some type of notation.
You kind of got on it here. I like this ... and the 63. This, I understand this.
Yeah, you can understand this, but this is still a little bit too much. What if instead we just wrote?
Mathematicians love being efficient, right? They're lazy.
They have things to do. They have to go home and count grains of rice.
Right.
This is yeah. So that is take 63 2's and multiply them all together.
This is the first square on our board. We have one grain of rice.
Yep.
And when we double it, we have 2 grains of rice.
Yep.
And we double it again, we have 4. And I'm thinking, this is similar to what we were doing. It's just represented differently.
Yeah, well, I mean, this one, the one you were making, right? Every time you're kind of adding these popsicle sticks, you're kind of branching out. One popsicle stick now becomes 2 popsicle sticks, and then you keep doing that. 1 popsicle stick becomes 2, but now you have 2 of them. So here you have 1. Now you have 1 times 2. Now each of these 2 branch into 2, so now you have 2 times 2, or you have 4 popsicle sticks. Every stage, every branch, you're multiplying by 2 again.
I basically just continue splitting, just like the tree does.
Yep.
Now I can really see what 2 to the power of 3 looks like.
And that's what we have here. 1 times 2 times 2 times 2, which is 8. This is 2 to the 3rd power.
When I see 2 to the power of something, let's just say n, n could also be number of steps up this tree. I could think about it that way.
Wow.
Yeah, you could view it. I guess one way to think about it is how many times you've branched. But that tree there is actually even more interesting.
I don't think this counts because, again, like this branch is 4 times, at each branch.
Well, I guess why not? I mean, well, it's different. It's not going to be 2 anymore. So the first one where you haven't branched yet, this is going to be 4 to the 0 power. You've had no branches yet. This, you branched once, so now this is 4 to the first power. You have 4 branches. And now each of those. So now you've branched twice, so now this is 4 to the second power. So yeah, the base, or what's called the base when you're taking an exponent, is 4 right over here. This is how many new branches each of the branches turn into at each of these, I guess, junctions, you could say.
Let's call them
Junctions. You haven't branched yet. Here you branched once, and here you branched twice.
But this is interesting. This is also why when I look at a tree, you know, there's thousands of leaves, but just one trunk. And when you actually go up and you look inside the tree, it only branches, you know, 3 or 4 times.
And that shows the power of exponential growth.
Yes.
You already know that we can view multiplication as repeated addition. So if we had 2 times 3, we could literally view this as 3 2's being added together. So it could be 2 plus 2 plus 2. Notice this is 1, 2, 3 2's, and when you add those 2's, you get 6. What we're going to introduce you to in this video is the idea of repeated multiplication, a new operation that really can be viewed as repeated multiplication, and that's the operation of taking an exponent. Exponent. And it sounds very fancy, but we'll see with a few examples that it's not too bad. So now let's take the idea of 2 to the third power, which is how we would, let me write this down in the appropriate colors. So 2 to the third power. So you might be tempted to say, hey, maybe this is 2 times 3, which would be 6. But remember, I just said this is repeated multiplication. So if I have 2 to the third power, this literally means multiplying 3 2's. So this would be equal to, not 2 plus 2 plus 2, but 2 times, I'll use a little dot for multiplication, 2 times 2 times 2. Well, what's 2 times 2 times 2? Well, that is equal to 8. So that is equal to 8. So 2 to the third power is equal to 8. Let's try a few more examples here. What is 3? What is 3 to the second power going to be equal to? And I'll let you think about that for a second. I encourage you to.
It's going to be 9.
So let's think it through. This literally means multiplying 2 3's. So let's multiply 3. Let me do that in yellow color. Let's multiply 3 times 3. So this is going to be equal to 9. Let's do a few more examples. What is, say, 5 to the, say 5 to the fourth power. And what you'll see here is this number is going to get large very fast. So 5 to the fourth power is going to be equal to multiplying 4 5s. So 5 times 5 times 5 times 5. Notice we have 1, 2, 3, 4 5s, and we are multiplying them. We are not adding it. This is not 5 times 4. This is not 20. This is 5 times 5 times 5 times 5. So what is this going to be?
625, I
Well,
guess.
5 times 5 is 25. 25 times 5 is 125. 125 times 5 is 625.
Cool. Okay, that's pretty fast. Okay. Your exponent exponent in base looks like a number small number is involved with the derived from single exponent. The number in the exponent is called the base. In this example, the base is 7 and the exponent is 5. And the exponent has to multiply the base by itself the number of times. In our example 4, it also multiplies 4 by itself 3 times. Once we write out the multiplication problem, we can easily evaluate the expression. Let's do this for the example we've been working on. The main reason we use exponent is because it's a shorter way to write out big numbers. For example, let's say we want to write the following, to express the following. That's really wrong to write. My hands just hurt from typing. Instead, we see that 2 is multiplied by itself 6 times. This means we can write the same thing with 2 as the base and 6 as the exponent. Cool. Let's make sure we understand exponents by trying some practice problems. How do I write as an exponent? Holy shit, I don't know. This thing? Oh, cool, okay. Oh shit. Oh. No, I didn't mean that.
What up?
Wait, intro to exponents. Can I just do, oh cool, okay. Check. Actually 6. The 4th power. Wow, okay. Whoa, I almost fell for that. Okay, cool. Challenge set. Complete the inequality. Holy shit, this is hard. 25? It's gonna be the 2. 18. Oh wow, okay. 27, 8. Oh my god. It's 10. Wait, so 9, negative 9. Oh my god, I'm an idiot. Oh shit, it's 2 to the 3rd power. Okay. I thought it was 3 to the 3rd. Okay, so this is actually 4 and 8, so we have 10. 64. Oh wow, I guess the 10 is larger. How much is it evaluate though? Wow, 1024, cool. Okay, let's start by taking a look at an example evaluating 3 squared, 3 squared. Here's a question to make sure you got that. What does it mean to square a number? Multiply the number by itself. Connection to a square. Finding 3 squared, 3 squared, is the same as finding the area of a square with side length 3. Okay. Oh wow, this is insane. Oh my god, this is getting hard. Nice. Challenge set. Oh wow. Evaluate. It's gonna be 16 plus 692. Order the from the least to greatest. Okay, this is 10. This is 25. This is 36 minus 6. That's 30. Okay. Next video. The 0 and 1st power.
What I want to do in this video is think about exponents in a slightly different way that will be useful for different contexts, and also go through a lot more examples. So the last
recording, man. Yeah, I am. My hair
video we saw that taking something to an exponent means multiplying that number that many times. So if I had the number, taking something to an exponent means multiplying that number examples. So the last video we saw that taking something to an exponent means multiplying that number that many times. So if I had the number negative 2 and I want to raise it to the 3rd power, this literally means taking 3 negative 2's. So this literally means taking 3 negative 2's, so negative 2, negative 2, and negative 2, and then multiplying them. And then multiplying them. So what's this going to be? Well, let's see. Negative 2 times negative 2 is positive 4. And then positive 4 times negative 2 is negative 8. So this would be equal to, negative 8. Now another way of thinking about exponents, instead of saying you're just taking 3 negative 2's and multiplying it, this is a completely reasonable way of viewing it. You could also view it as this is the number of times you're going to multiply this number times 1. So you could completely view this as being equal to, so you're going to start with a 1, and you're going to multiply 1 times negative 2 3 times. So this is times negative 2 times negative 2 times negative 2. So clearly these are the same number. Here we just took this and we're just multiplying it by 1, so you're still going to get negative 8. And this might be a slightly more useful idea to get an intuition for exponents, especially when you start taking things to the 1 or 0 power. So let's think about that a little bit. What is 2? What is positive 2 to the, based on this definition, to the 0 power going to be equal to? To the 0 power going to be equal to? Well, we just said, this says how many times are you going to multiply 1 times this number. So this literally says, I'm going to take a 1, I'm going to take a 1, and I'm going to multiply it by 2 0 times. Well, if I'm going to multiply it by 2 0 times, that means I'm just left with the 1. So 2 to the 0 power is going to be equal to 1. And actually, any non-zero number to the 0 power is 1 by that same rationale. And I'll make another video that will also give a little bit more intuition on it. That might seem very counterintuitive, but it's based on one way of thinking about it is thinking of an exponent as this. And this will also make sense if we start thinking of what 2 to the first power is. So 2 to the first power. So let's go to this definition we just gave of the exponent. We always start with a 1, and we multiply by the 2 one time. So 2 is going to be 1. We're only going to multiply it by the 2. I'll use this for multiplication. I'll use the dot. We're only going to multiply it by 2 one time. So 1 times 2, well, that's clearly just going to be equal to 2. And any number to the first power is just going to be equal to that number. And then we can go from there, and you'll, of course, see the pattern. If we say what 2 squared is, 2 squared, well, based on this definition, we start with a 1, and we multiply it by 2 times. So times 2 times 2 is going to be equal to 4. And we've seen this before. You go to 2 to the third, 2 to the third power. You start with a 1, and then multiply it by 2 3 times. So times 2 times 2 times 2. This is going to give us positive 8. And you probably see a pattern here. Every time we multiply by 2, or every time I should say we raise 2 to a 1 more power, we are multiplying by 2. Notice this. To go from 2 to the 0 to 2 to the 1, we multiplied by 2. I'll use a little x for the multiplication symbol now, the little cross. And then to go from 2 to the first power to 2 to the second power, we multiply by 2. Multiply by 2 again. And that makes complete sense because this is literally telling us how many times are we going to take this number and how many times are we going to take 1 and multiply it by this number. And so when you go from 2 to the second power to 2 to the third, you're multiplying by 2 one more time. And this is another intuition of why something to the 0 power is equal to 1. If you were to go backwards, if say we didn't know what 2 to the 0 power is and we were just trying to figure out what would make sense. When we go from 2 to the third power to 2 to the second, we'd be dividing by 2. We're going from 8 to 4. Then we divide by 2 again to go from 2 to the second to 2 to the first. And then maybe it seems like we should just divide by 2 again from going from 2 to the first to 2 to the 0. And that would give us 1.
Cool.
Let's think about exponents with 1s and 0s. So let's take the number 1 and let's raise it to the 8th power. So we've already seen that there's 2 ways of thinking about this. You could literally view this as taking 8 ones and then multiplying them together. So let's do that. So you have 1, 2, 3, 4, 5, 6, 7, 8 ones, and then you're going to multiply them together. And if you were to do that, you would get, well, 1 times 1 is 1 times 1. It doesn't matter how many times you multiply 1 by 1, you are going to just get 1. You are just going to get 1. And you could imagine, I did it 8 times, I multiplied 8 ones, but even if this was 80, or if this was 800, or if this was 8 million, if I just multiplied 1, if I had 8 million ones, and I multiplied them all together, it would still be equal to 1. So 1 to any power is just going to be equal to 1. You would say, hey, what about 1 to the 0th power? 1 to the 0th power. Well, we've already said anything to the 0th power, except for 0, it's actually up for debate, but anything to the 0th power is going to be equal to 1. And just as a little bit of intuition here, you could literally view this as our other definition of exponentiation, which is you start with a 1, and this number says how many times you're going to multiply that 1 times this number. So 1 times 1, 0 times, is just going to be 1. And that was a little bit clearer when we did it like this, where we said 2 to the, let's say, 4th power, 2 to the 4th power, is equal to, this was the other definition of exponentiation we had, which is you start with a 1, and then you multiply it by 2 4 times. So times 2, times 2, times 2, times 2, which is equal to, let's see, this is equal to 16. So here, if you start with a 1, and then you multiply it by 1 0 times, you're still going to have that 1 right over there. That's why anything that's not 0 to the 1 power is going to be equal to 1. Now let's try some other interesting scenarios. Let's try some negative numbers. So let's take negative 1, and let's first raise it. Let's first raise it to the 0 power. So once again, this is just going based on this definition. This is starting with a 1, and then multiplying it by this number 0 times. Well, that means we're just not going to multiply it by this number, so you're just going to get a 1. Let's try negative 1. Let's try negative 1 to the first power. Well, anything to the first power, you could view this, and I like going with this definition as opposed to this one right over here. If we were to make them consistent, if you were to make this definition consistent with this, you would say, hey, let's start with a 1, and then multiply it by 1 8 times, and you're still going to get a 1 right over here. But let's do this with negative 1. So we're going to start with a 1, and then we're going to multiply it by negative 1 1 time. Times negative 1, and this is, of course, going to be equal to negative 1. Now, let's take negative 1, and let's take it to the second power. We often say that we are squaring it when we take something to the second power. So negative 1 to the second power. Well, we could start with a 1. We could start with a 1, and then multiply it by negative 1 2 times. Multiply it by negative 1. Multiply it by negative 1 twice. And what's this going to be equal to? And once again, by our old definition, you could also just say, hey, ignoring this one, because that's not going to change the value, we took 2 negative 1s, and we're multiplying them. Well, negative 1 times negative 1 is 1. And I think you see a pattern forming. Let's take negative 1. Let's take negative 1 to the third power. To the third power. What's this going to be?
If a negative number is raised to an
well, by this definition, you start with a 1, and then you
result.
multiply it by negative 1 3 times.
You get a positive result.
Negative 1 times negative
number
1
raised to an even
times
number
negative 1.
positive.
Or you could just think of it as you're taking 3 negative 1s and you're multiplying it, because this 1 doesn't change the value. And this is going to be equal to negative 1 times negative 1 is positive 1 times negative 1 is negative 1. So you see the pattern. Negative 1 to the 0th power is 1. Negative 1 to the first power is negative 1. Then you multiply by negative 1 again to get positive 1. Then you multiply by negative 1 again to get negative 1. And the pattern you might be seeing is if you take negative 1 to an odd power, you're going to get a negative 1. And if you take it to an even power, you're going to get 1. You're going to get 1, because a negative times a negative is going to be the positive, and you're going to have an even number of negatives, so you're always going to have negative times negatives. So this right over here, this is even. Even is going to be positive 1. And you could see that if you went to negative 1 to the 4th power. Negative 1 to the 4th power, well, you could start with a 1, and then multiply it by negative 1 4 times. So negative 1 times negative 1 times negative 1 times negative 1, which is just going to be equal to positive 1. So if someone were to ask you, we already established that if someone were to take 1 to the, 1 millionth power, this is just going to be equal to 1. It's just going to be equal to 1. If someone told you, let's take negative 1 and raise it to the 1 millionth power,
Positive 1.
1 millionth power. Well, 1 million is an even number, so this is still going to be equal to positive 1. But if you took negative 1, to the 999,999th power, this is an odd number. So this is going to be equal to negative 1.
Well, let's go. That's pretty cool.
Let's think of
Wow.
So let's think of a little bit about powers of 0. So what do you think 0 to the first power is going to be? And I encourage you to pause this video. Well, let's just think about it. One definition of exponentiation is that you start with a 1, and then you multiply this number times the 1 time. So this is literally going to be 1 times, let me do it in the right colors, 1 times 0. You're multiplying the 1 by 0 1 time. 1 times 0, well, that's just going to be equal to 0. Now, what do you think 0 squared, or 0 to the second power, is going to be equal to? Well, once again, one way of thinking about this is that you start with a 1, and we're going to multiply it by 0 2 times. So times 0 times 0. Well, what's that going to be? Well, you multiply anything times 0, once again, you are going to get 0. And I think you see a pattern here. If I take a 0 to any non-zero number, so to the power of any non-zero, so there's some non-zero number, then this is going to be equal to 0. This is going to be equal to 0. Now, this raises a very interesting question. What happens at 0 to the 0th power? So here, 0 to the millionth power is going to be 0. 0 to the trillionth power is going to be 0. Even negative or fractional exponents, which we haven't talked about yet. As long as they're non-zero, this is just going to be fractional exponents, which we haven't talked about yet. As long as they're non-zero, even negative or fractional exponents, which we haven't talked about yet. As long as they're non-zero, this is just going to be fractional exponents, which we haven't talked about yet. As long as they're non-zero, this is just going to be equal to 0. Kind of makes sense. But now let's think about what 0 to the 0th power is, because this is actually a fairly deep question. And I'll give you a hint. Well, actually, why don't you pause the video and think a little bit about what 0 to the 0th power should be. Well, there's two trains of thought here. You could say, look, 0 to some non-zero number is 0. So why don't we just extend this to all numbers and say 0 to any number?
Judging from the previous logic, like if there's 1 and then you multiply it by nothing, then you're still left 1. But still, that's so strange, because
number should be 0. And so maybe you should say that 0 to the 0th power is 0. But then there was another train of logic that we've already learned, that any non-zero number, so non-zero number, if you take any non-zero number and you raise it to the 0th power, we've already established that this is, you start with a 1 and you multiply it times that non-zero number 0 times. So this is always going to be equal to 1 for a non-zero number. So this is always going to be equal to 1. So maybe you say, hey, maybe we should extend this to all numbers, including 0. So maybe 0 to the 0th power should be 1. So we could make the argument that 0 to the 0th power should be equal to 1. So you see a conundrum here, and there's actually really good cases. You can get actually fairly sophisticated with your mathematics, and there's really good cases for both of these, for 0 to 0th being 0, and 0 to the 0th power being 1. And so when mathematicians get into this situation where they say, well, there's good cases for either, there's not a completely natural one, either of these definitions would lead to difficulties in mathematics. And so what mathematicians have decided to do is, for the most part, and you'll find people who will dispute this, people who say, no, I like one more than the other, but for the most part, this is left undefined. 0 to the 0 is not defined by, at least just kind of more conventional mathematics. In some use cases, it might be defined to be one of these two things. So 0 to any non-zero number, you're going to get 0. Any non-zero number to the 0th power, you're going to get 1. But 0 to the 0, that's a little bit of a question mark.
Dang.
So let's think of a little bit about powers of 0. So we are asking 0 asked to order the expressions from least to greatest. And this is from the exercises on Khan Academy. And if we're doing it on Khan Academy, we would drag these little tiles around from least to greatest, least on the left, greatest on the right. I can't drag it around because this is just a picture. So I'm going to evaluate each of these, and then I'm going to rewrite them from least to greatest. So let's start with 2 to the third minus 2 to the first. What is that going to be? 2 to the third minus 2 to the first. And if you feel really confident, just pause this video and try to figure out the whole thing. Order them from least to greatest.
Okay, this one's going to be 6, this one's going to be 5, this one's going to be 9.
Well, 2 to the third, that is 2 times 2 times 2. And then 2 to the first, well, that's just 2. So 2 times 2 is 4, times 2 is 8, minus 2. This is going to be equal to 6. So this expression right over here could be evaluated as being equal to 6. Now, what about this right over here? What is this equal to? Well, let's see. We have 2 squared plus 3 to the 0. 2 squared is 2 times 2. And anything to the 0 power is going to be equal to 1. It's an interesting thing to think about what 0 to the 0th power should be, but that'll be a topic for another video. But here we have 3 to the 0th power, which is clearly equal to 1. And so we have 2 times 2 plus 1. This is 4 plus 1, which is equal to 5. So the second tile is equal to 5. And then 3 squared. Well, 3 squared, that's just 3 times 3. 3 times 3 is equal to 9. So if I were to order them from least to greatest, the smallest of these is 2 squared plus 3 to the 0th power. That one is equal to 5, so I put that on the left. Then we have this thing that's equal to 6, 2 to the 3rd power minus 2 to the 1st power. And then the largest value here is 3 squared. So we would put that tile, 3 squared, we will put that tile on the right. And we're done.
Wow.
What we're going to do in this video is get some practice evaluating exponents of decimals. So let's say that I have 0.2 to the 3rd power. Pause this video, see if you can figure out what that is going to be. Well, this would just mean if I take something to the 3rd power, that means I take 3 of that number and I multiply them together. So it's 0.2 times 0.2 times 0.2. Well, what is this going to be equal to? Well, if I take 0.2 times 0.2, that is going to be 0.04. One way to think about it, 2 times 2 is 4. And then I have one number behind the decimal to the right of the decimal here. I have another digit to the right of the decimal right over here. So my product is going to have 2 digits to the right of the decimal. So it would be 0.04. And then if I were to multiply that times 0.2, so if I were to multiply that together, what is that going to be equal to? Well, 4 times 2 is equal to 8. And now I have 1, 2, 3 numbers to the right of the decimal point. So my product is going to have 1, 2, 3 numbers to the right of the decimal point. So now that we've had a little bit of practice with that, let's do another example. So let's say that I were to ask you, what is 0 0.9 squared. Pause this video and see if you can figure that out.
0.81.
All right, well, this is just going to be 0.9 times 0.9. And what's that going to be equal to? Well, you could just say 9 times 9 is going to be equal to 81. And so, let's see, in the two numbers that I'm multiplying, I have a total of 2 numbers, or 2 digits, to the right of the decimal point. So my answer is going to have 2 digits to the right of the decimal point. So I'd put the decimal right over there, and I'll put the 0, so 0.81. Another way to think about it is 9/10 of 9/10 is 81 hundredths. But there you go. Using exponents or taking exponents of decimals, it's the same as when we're taking it of integers. It's just in this case, you just have to do a little bit of a decimal multiplication.
Okay.
We're asked to evaluate the expression 5 to the x power minus 3 to the x power for x equals 2. So pause this video and see if you can figure out what does this expression equal when x equals 2. All right, now let's work through this together. So what we want to do is everywhere we see an x, we want to replace it with a 2. So this expression for x equals 2 would be 5 to the second power minus 3 to the second power. Well, what's that going to be equal to? Well, 5 to the second power, that's the same thing as 5 times 5. And then from that, we are going to subtract 3 times 3. 3 times 3. And now order of operations would tell us to do the multiplication or do the exponents first, which is this multiplication. But just to make it clear, I'll put some parentheses here. And this is going to be equal to 5 times 5 is 25 minus 9, which is equal to, what's 25 minus 9? It is equal to 16. So that's what that expression equals for x equals 2. Let's do another example. So now we are asked, what is the value of y squared minus x to the 4th when y is equal to 9 and x equals 2? So once again, pause this video and see if you can evaluate that. All right, so here we have variables as the bases as opposed to being the exponents, and we have 2 different variables. But all we have to do is wherever we see a y, we substitute it with a 9, and wherever we see an x, we substitute.
80, then minus 10 from 70 minus 6. 80 minus 6, 74, 75.
It with a 2. So y squared is going to be the same thing as 9 squared minus x, which is 2. That minus looks a little bit funny. Let me see. So this is going to be 9 squared minus x, which is 2 to the 4th power. Now what is this going to be equal to? Well, 9 squared is 9 times 9. So this whole thing is going to be equal to 81. This whole thing right over here is 9 times 9. 9 times 9 is that right over there. And then from that, we're going to subtract 2 to the 4th power. Well, what's 2 to the 4th power? That is 2 times 2 times 2 times 2. So this is going to be 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. So it's 81 minus 16. Now what is that going to be equal to? Let's see, 81 minus 6 is 75, and then minus another 10 is going to be 65. So there you have it. Y squared minus x to the 4th, when y is equal to 9 and x equals 2, is equal to 65.
Holy shit, did I just say 75? Oh my god, I'm an idiot. I mean, like 80 minus 10 is 70. Why did I say 80? I'm a fucking idiot. I've confirmed that I'm clearly an idiot. Irrespective of an exponent and the basics like 4 to the 3rd power. Above and to the right of a number is called an exponent number. An exponent is similar to itself. So, wait. I feel like I've seen these before. Oh, no, okay. No, let's just start it. 1 Take no, not the quiz. Just 5 questions. No. Exponents basic. Oh, what? Oh my god, I don't know. Let's say 1 1 1. No, actually 0 1 1. Oh, 1 2 1 2. 1 2 3 4 5 6 7. Is it 0 7? 2 3 4 5 6 7. Okay, cool. It's this 4 times 4 16 64. Oh my god, this 4 here is a debate. Let's go. Okay, so this one's 36. The other one's like 16, 64. Okay. Oh wow, that's insane. 4 9 16 81. Oh, this is hard. I don't know whether this question is true or false. It's false. Oh, it's false too. Everything's false. It's weird. Okay, what is this? This is 49. Oh, this is 27 times 3, so it's clearly yeah. 1. Oh my god, this is hard. It's gonna be 1/16 actually. Alright, 1/16. Cool. Which are expressions true or false? 1 2 3 false. I mean, if this is actually could be true. If this is by 2, then you get 100. But it's 3, so okay. This is actually 64 actually, and then 8 times 8 is 64. Okay, that's true. Oh my god, this is 36, and this one's false. Can't be. With variable expressions with exponents. Ident 3, okay. 3 is gonna 7, 4, 364, and yeah. Okay, it's gonna be 81. Oh my god, times 9. Insane. Okay, 81 times 9. Get 9 and 72. 79. What is the value of x cubed and x to the 4th raised to 4? Oh wow, this is actually y. Cool. 27, 81, and then y 0, and 81 still. I'm wrong. What the fuck? Y is 0. Oh my god, it's 0. Oh. Oh, god damn. I deserve that loss. I'm gonna repeat. Okay. This is 25. That's right, correct. 25. This one is 5. Okay. Oh my god, this is hard. Okay. 2 times 2 times 2 times 2 times 2. 4, 8, 16, 32. 32 minus 25. 7. X to 6th. Okay, it's gonna be 1 plus 121. So 122. Okay. It's gonna be 9. Gonna have 3. Evaluate expression x cubed minus 3 plus x. Wow, this is cool. Okay. 4 times 4, 16, 64 minus 7 squared 49. So let's add 1 to both. So we get 65 minus 50. We get 15. Yeah, 15. Okay, let's do the quiz. This is this one. Oh wow, this is hard. That's 1. But in this kind of form, I guess. Cool. What is the value of x currently? Okay. X is 3, 9, 27 plus 4, 16, 64, 7. It's gonna be 11, 91, bro. I always get some trouble with this one. 7 plus 4. Although I know it's 11. Just to be sure. This one's 64, this one's 27. Okay, cool. That's 81. It's 32. Okay, it's larger. It's larger. Great. We're done with that. 46 minutes in. God damn, my hair sucks. I don't care. Okay, let's do square roots.
If you're watching a movie and someone is attempting to do fancy mathematics on a chalkboard, you'll almost always see a symbol that looks like this radical symbol. And this is used to the square root, and we'll see other types of roots as well. But your question is, well, what does this thing actually mean? And now that we know a little bit about exponents, we'll see that the square root symbol or the root symbol or the radical is not so hard to understand. So let's start with an example. So we know that 3 to the second power is what? 3 squared is what? Well, that's the same thing as 3 times 3. That's going to be equal to 9. But what if we went the other way around? What if we started with a 9 and we said, well, what times itself is equal to 9? We already know that answer is 3. But how could we use a symbol that tells us that? So, well, as you can imagine, that symbol is going to be the radical here. So we could write the square root of 9. And when you look at this way, you say, okay, what squared is equal to 9? And you would say, well, this is going to be equal to 3. This is going to be equal to 3. And I want you to really look at these two equations right over here, because this is the essence of the square root symbol. If you say the square root of 9, you're saying what times itself is equal to 9. And, well, that's going to be 3. And 3 squared is equal to 9. I can do that again. I can do that many times. I can write 4 squared is equal to 16. Well, what's the square root of 16 going to be? Well, it's going to be equal to 4. Let me do it again. And actually, let me start with the square root. What is the square root of 25 going to be? Well, this is the number that times itself is going to be equal to 25, or the number where if I were to square it, I get to 25. Well, what number is that? Well, that's going to be equal to 5. Why? Because we know that 5 squared is equal to 25. Now, I know that there's a nagging feeling that some of you might be having, because if I were to take -3 and square it, I would also get +9. And the same thing, if I were to take -4 and I were to square the whole thing, I would also get +16, or -5, and if I were to square it, I would also get +25. So why couldn't this thing right over here, why can't this square root be +3 or -3? Well, depending on who you talk to, that's actually a reasonable thing to think about. But when you see a radical symbol like this, people usually call this the principal root. Principal root. Principal square root. Square root. And another way to think about it, it's the positive. This is going to be the positive square root. If someone wants the negative square root of 9, they might say something like this. They might say the negative. Let me scroll up a little bit. They might say something like the negative square root of 9. Let me scroll up a little bit. They might say something like the negative square root of 9. Well, that's going to be equal to negative 3. And what's interesting about this is, well, if you square both sides of this equation, if you were to square both sides of this equation, what do you get? Well, anything negative squared becomes a positive. And then the square root of 9 squared, well, that's just going to be 9. And on the right-hand side, negative 3 squared, well, negative 3 times negative 3 is positive 9. So it all works out. 9 is equal to 9. And so this is an interesting thing. Actually, let me write this a little bit more algebraically now. If we were to write the principal root of 9 is equal to x. There's only one possible x here that satisfies it, because the standard convention, what most mathematicians have agreed to view this radical symbol as, is that this is the principal square root. This is the positive square root. So there's only one x here. There's only one x that would satisfy this, and that is x is equal to 3. Now, if I were to write x squared is equal to 9, now this is slightly different. X equals 3 definitely satisfies this. This could be x equals 3. But the other thing, the other x that satisfies this is x could also be equal to negative 3, because negative 3 squared is also equal to 9. So these two things, these two statements are almost equivalent, although when you're looking at this one, there's two x's that satisfy this one, while there's only one x that satisfies this one, because this is the positive square root. If people wanted to write something equivalent where you would have two x's that could satisfy it, you might see something like this: plus or minus square root of 9 is equal to x, and now x could take on positive 3 or negative 3.
We're asked to find the square root of 100. Let me write this down bigger. So the square root is this big check-looking thing. The square root of 100. And when you see it like this means the positive square root. If you're familiar with negative numbers, you know that there's also a negative square root. But when you just see this symbol, that means the positive square root. So let's think about what this is saying. This is asking us to find the number, the positive number, that when I multiply that number by itself, I get 100. So what number when I multiply by itself do I get 100? Let's see, if I multiply 9 by itself, that's only going to be 81. If I multiply 10 by itself, that is 100. So this is equal to, and let me write it this way. Normally you could skip this step, but you could write this as the square root of, and instead of 100, 100 is the same thing as 10 times 10. And then you know the square root of something times itself, that's just going to be that something. This is just equal to 10. So the square root of 100 is 10. Or another way you could write, I guess, the same truth is that 10 squared, which is equal to 10 times 10, is equal to 100.
That's so weird. Let me face this. Okay. Damn, it's a lot of number. Wow, okay, number greater than 9. What's no next? Okay.
We are asked to approximate the principal root, or the positive square root of 45, to the hundredths place. And I'm assuming they don't want us to use a calculator, because that would be too easy. So let's see if we can approximate this just with our pen and paper right over here. So square root of 45. So the square root of 45, or the principal root of 45. 45 is not a perfect square.
Yep.
It's definitely not a perfect square, but we know, let's see, what are the perfect squares around it? We know that it is going to be less than, the next perfect square above 45 is going to be, let's see, it'll be 49, because that is 7 times 7. So it's less than the square root of 49, and it's greater than the square root of 36. And so the square root of 36, the principal root of 36, I should say, is 6, and the principal root of 49 is 7. So this value right over here is going to be between, it's going to be between 6 and 7. And if we look at it, it's only 4 away from 49, and it's 9 away from 36. So it looks like, so the difference between 36 and 49 is, it's 13. So it's a total 13 gap between the 6 squared and 7 squared. And this is 9 of the way through it. So just as a kind of approximation, maybe, and it's not going to work out perfectly because we're squaring it. This isn't a linear relationship. But it's going to be closer to 7 than it's going to be to 6. And at least the square, or the 45, is 9/13 of the way. So we could try, let's see, it looks like well, that's about 2/3 of the way. So let's try 6.7. Let's try 6.7 as a guess, just based on 0.7 is about 2/3. It looks like about the same. Actually, we could calculate this right here if we want. Actually, let's do that just for fun. So 9/13 as a decimal is going to be what? It's going to be 13 into 9. We're going to put some decimal places right over here. 13 doesn't go into 9. 13 does go into 90. And it goes into 90. Let's see, does it go into it 7 times? It goes into it 6 times. So 6 times 3 is 18. 6 times 1 is 6. Plus 1 is 7. And then you subtract. You get 12. So it went into it almost exactly 7 times. So this value right here is almost 0.7. And so if you say how many times does 13 go into 120, it looks like it's like 9 times. Yeah, it would go into it 9 times. 9 times. 9 times 3, get rid of this. 9 times 3 is 27. 9 times 1 is 9, plus 2 is 11. You have a remainder of 3. So you get, it's about 0.69. So 6.7 would be a pretty good guess. This is 0.69 of the way between 36 and 49. So let's go roughly 0.69 of the way between 6 and 7. So this is, once again, just to approximate. It's not necessarily going to give us the exact answer. We have to use that as to make a good initial guess and then see how well it works. So let's try 6.7.
6.7.
Let's try 6.7. And the really way to try it is to square 6.7. So 6.7 times 6. Maybe I'll write the multiplication symbol there. 6.7 times 6.7. So we have 7 times 7 is 49. 7 times 6 is 42. Plus 4 is 46. Put a 0 now because we're now moved up. We've moved a space to the left. So now we have 6 times 7 is 42. Carry the 4. 6 times 6 is 36. Plus 4 is 40. And so 9 plus 0 is 9. 6 plus 2 is 8. 4 plus 0 is 4. And Then we have a 4 right over here, and we have 2 total numbers behind the decimal point, 1, 2. So this gives us 44.89. So 6.7 gets us pretty close, but we're still not probably right to the hundredth. Well, it's definitely not to the hundredths place. We've only gone to the tenths place right over here. So if we want to get to 45, this 6.7 squared is still less than the square root, or I should say 6.7 squared is still less than 45, or 6.7 is still less than the square root of 45. So let's try 6.71. So let's try let me do this in a new color. I'll do 6.71 in pink. So let's try 6.71. Increase it a little bit. See if we can go from 44.89 to 45, because this is really close already. And if this is, well, let's just try it out. 6.71. So once again, we have to do some arithmetic by hand. We are assuming that they don't want us to use a calculator here. So if 1 times 1 is 1, 1 times 7 is 7, 1 times 6 is 6. Put a 0 here. 7 times 1 is 7. 7 times 7 is 49. 7 times 6 is 42, plus 4 is 46. And then we have 2 zeros here. 6 times 1 is 6. 6 times 7 is 42. We have this new 4 here. 6 times 6 is 36. Plus 4 is 40. Plus 40. So if you really, well, it's interesting to think what we got incrementally by adding that 100th over there. Because this part over here, well, we'll see actually when we add all of this up. You get a 1. 7 plus 7 is 14. 1 plus 6 plus 9 is 16. Plus 6 is 22. 2 plus 6 plus 2 is 10. And then 1 plus 4 is 5. And then we bring down the 4. And we have 1, 2, 3, 4 numbers behind the decimal point. 1, 2, 3, 4. So when we squared 6.71, 6.71 squared is equal to 45.0241. So 6.71 is a little bit greater. So let me make it clear now. We know that 6.7 is less than the square root of 45. And we know that that is less than 6.71. Because when we square this, we get something a little bit over the square root of 45. But the key here is when we squared this, so 6.7 squared, so 6.7 squared got us 44.89, which is 11 hundredths away from 45. So this is, and then if we look at 6.71 squared, we're only 2.4 hundredths above 45. So this right here is closer to the square root of 45. So if we approximate to the hundredths place, definitely want to go with 6.745. So if it's above 45, so this right here is closer to the square root of 45. So if we approximate to the hundredths place, definitely want to go with 6. And then if we look at 11 hundredths away from 45.
11 hundredths.
So this is, and then if we look at 6.71 squared, we're only 2.4 hundredths above 45. So this right here is closer to the square root of 45. So if we approximate above 45, so this right here is closer to the square root of 45. So if we approximate to the hundredths place, definitely want to go with 6.71.
Damn, it's a lengthy process.
We are asked to
boomer on a boomer live stream. There's got to be an easier way. Just for fun.
Let's see if we can simplify 5
I've been recording an hour.
Times the square root of 117. 117. So 117 doesn't jump out at me as some type of a perfect square. So let's actually take its prime factorization and see if any of those prime factors show up more than once. So it's clearly it's an odd number. It's clearly not divisible by 2. To test whether it's divisible by 3, we can add up all of the digits, and we explain why this works in another place on Khan Academy. But if you add up all the digits, you get a 9. And 9 is divisible by 3, so 117 is going to be divisible by 3. Now let's do a little aside here to figure out what 117 divided by 3 actually is. So 3 doesn't go into 1. It does go into 11 3 times. 3 times 3 is 9. Subtract. You got a remainder of 2. Bring down a 7. 3 times, okay, 3 goes into 27 9 times. 9 times 3 is 27. Subtract and you're done. It goes in perfectly. And so so we can factor 117 as 3 times 39. Now 39 we can factor as, that jumps out more at us, that's divisible 13. By 3. That's equivalent to 3 times 13, and then all of these are now 13. Prime numbers. So we could say that this thing is the same as 5 times the square root of 3 times 3, 3 times 3, 3 times 3 times 13, times 13. And this is going to be the same thing as, and we know this from our exponent properties, as 5 times the square root of 3 times 3, 5 times the square root of 3 times 3, times the square root of 13. Now, what's the square root of 3 times 3? Well, that's the square root of 9. That's the square root of 3 squared. Any of those, well, that's just going to give you 3. So this is just going to simplify to 3. So this whole thing is 5 times 3 times the square root of 13.
Wow.
So this part right over here would give us 15 times the square root of 13. Let's do one more example here. So let's try to simplify 3 times the square root of 26. Actually, 26 in yellow like I did in the previous problem. 26. Well, 26 is clearly an even number, so it's going to be divisible by 2. We can rewrite it as 2 times 13. And then we're done. 13 is a prime number. We can't factor this anymore. And so 26 doesn't have any perfect squares in it. It's not like we can factor it out as a factor of some other numbers and some perfect squares like we did here. 117 is 13 times 9. It's the product of a perfect square and 13. 26 isn't. So we've simplified this about as much as we can. We would just leave this as 3 times the square root of 26. Like we did here. 117 is 13 times 9. It's the product of a perfect square and 13. 26 isn't. So we've simplified this about as much as we can. We would just leave this as 3 times the square root of 26.
And we're done. We're done. The square root of a number is a factor we can multiply to the number. The number is check thing. Find the square root of a number is what the square. It's the opposite of squaring a number. Yep, true. If the square root is a whole number, it is full of the perfect square. Okay. Perfect square would be whole numbers. When the result of that is a whole number, it's a perfect square. If we can figure out what the factor multiplied by itself is in the given number, we can make a factor of 3. Okay. 2 times 3, 6. Okay. So this is 11. Square roots. Wait, what? Okay, cool. Oh shit. Approximating square roots, man. Without using just up. Oh man, it's gonna be 100. Between 10. Oh shit, this video this too, but it said it's this one. Let's see how we solve this shit. Okay. Oh, okay. Oh, okay. What? Yo, what the fuck? This is so weird. What? Yo, this negative number. How is this incorrect? How the hell is this incorrect? That is so weird. Fill in the blanks with two consecutive integers to complete the following. Oh, consecutive integers. Holy shit. Okay, let's do 181. How do I do this? What's the closest? Okay, so let's do 14. It's 14. Oh, it's gonna be 16. 4, 0, 4, 1. Actually, it's gonna be 5, 6, 12, 9, 1. Okay. Now we're following our from least to greatest. Okay, cool. This is 40. This is 36. Well, cool. But everything else, so the value. Not really. It should be this one. I think. Let's see. It's, yeah, I've already evaluated that. Let's do that one. God damn it! I made a mistake. Okay, so it's 9. Wait, what? I mean, 8 times 8 is 64. 8 to 1. So yeah, 4.5 and 5. Oh wow, okay. Since 10 and 11? 11's 1 to 1, so it's gonna be. Okay, 8 times 8, 64 is 49. Cool. Simplifying square roots. Let's go. Oh my god. Show calculator. Oh shit, I'm not supposed to do it like this, aren't I? Let's see, its factor of this is 515. Oh my god. Wait, what? Yo, okay. This is insane. Isn't it? Oh my god. So I can remove Oh no, why did it say 5? Should be just 3. Oh my god. Oh my gosh. 450 is 3 150, which is also like 350. And then for the 50 part, you got like 10 and 5. And this was like 2 and 5. So I guess I'm left with 5 times 5, 5, 15 square root of 2. Wow. Pretty cool. Okay. 200 is let's do 2 and 100, 2 and 50, 2 and 25, and then 5 and 5, so we got these two guys trying. Okay, so 5 and 10 times 20 squared root 2, please. Oh god, I got it wrong. Okay. 2 times 2 is 25, dude. 25, dude. Oh, shit. Times 4. 25 times 4 is 100, and we're left with 2. What the fuck? We're gonna do 100, 2, 50, 2, 95. It's like 5, 5, so we get 2 over here, we got 4, 95, it's gonna be 100, and you're left with 2, so what the fuck? Yo, what gives? For real? Square root of 200. 14? The fuck? Oh, it should be just 5. 5 times 2, 10. Oh my god. I'm out of my mind. I'm out of my mind. 180, 290, 245, 315, and 3 and 5, 6, 5. Okay, this is 725, I believe. Yep, and then 5. Oh man. Good. I'm gonna take a bit of a rest again. Although I don't want to rest. I don't want to rest. I'm gonna rest a bit. Okay, cool. I fixed the mic. Let's continue. Cube roots. Intro to cube roots.
We already know a little bit about square roots. For example, if I were to tell you that 7 squared is equal to 49, that's equivalent to saying that 7 is equal to the square root of 49. The square root essentially unwinds taking the square of something. In fact, we could write it like this. We could write the square root of 49. So this is whatever number times itself is equal to 49. If I multiply that number times itself, if I square it, well, I'm going to get 49.
Wow.
And that's going to be true for any number, not just 49. If I write this, if I write the square root of x, and if I were to square it, that's going to be equal to x. And that's going to be true for any x for which we can evaluate the square root, evaluate the principal root. Now, typically, and as you advance in math, you're going to see that this will change. But typically, you say, okay, if I'm going to take the square root of something, x has to be non-negative. X has to be non-negative. This is going to change once we start thinking about imaginary and complex numbers. But typically, for the principal square root, we assume that whatever's under the radical, whatever's under here, is going to be non-negative. Because it's hard to square a number, at least the numbers that we know about, it's hard to square them and get a negative number. So for this thing to be defined, for it to make sense, it's typical to say that, okay, we need to put a non-negative number in here. But anyway, the focus of this video is not on the square root. It's really just to review things so we can start thinking about the cube root. And as you can imagine, where does the whole notion of taking a square of something or a square root come from? Well, it comes from the notion of finding the area of a square. If I have a square like this, and if this side is 7, well, if it's a square, all the sides are going to be 7. And if I wanted to find the area of this, it would be 7 times 7. Or 7 squared. That would be the area of this. Now, or if I were to say, well, if I have a square, and that doesn't look like a perfect square, but you get the idea, all the sides are the same length. If I have a square with area x, if the area here is x, what are the lengths of the sides going to be? Well, it's going to be square root of x. All of the sides are going to be square root of x. So it's going to be square root of x by square root of x. And this side's going to be square root of x as well, and that's going to be square root of x as well. So that's where the term square root comes from, where the square comes from. Now, what do you think cube root? Well, same idea. If I have a cube, let me do my best attempt at drawing a cube really fast. If I have a cube, and a cube, all of its dimensions have the same length, so this is a 2 by 2 by 2 cube, what's the volume over here? Well, the volume is going to be 2 times 2 times 2, which is 2 to the third power, or 2 cubed. This is 2 cubed. That's why they use the word cubed, because this would be the volume of a cube where each of its sides have length 2. And this, of course, is going to be equal to 8. But what if we went the other way around? What if we started with the cube, or what if we started with its volume? What if we started with the cube's volume, and let's say the volume here is 8 cubic units. So volume is equal to 8. And we wanted to find the lengths of the sides. So we wanted to figure out what x is, because that's x, and that's x. It's a cube, so all its dimensions have the same length. Well, there's two ways that we could express this. We could say that x times x times x, or x to the third power, is equal to 8. Or we could use the cube root symbol, which is a radical with a little 3 in the right place. Or we could write that x is equal to, it's going to look very similar to the square root. This would be the square root of 8. But to make it clear that we're talking about the cube root of 8, we would write a little 3 over there. In theory, for square root, you could put a little 2 over here, but that'd be redundant. If there's no number here, people just assume that it's the square root. But if you're figuring out the cube root, or sometimes people say the third root, well, then you have to say, well, you have to put this little 3 right over here in this little notch in the radical symbol right over here. And so this is saying x is going to be some number that if I cube it, I get 8. So with that out of the way, let's do some examples. Let's say that I want to calculate the cube root of 27. What's that going to be? Well, if I say that this is going to be equal to x, this is equivalent to saying that x to the third, or that 27 is equal to x to the third power. So what is x going to be?
3.
Well, x times x times x is equal to 27. Well, the number I can think of is 3. So we would say that x, let me scroll down a little bit, x is equal to 3. Now let me ask you a question. Can we write something like, can we pick a new color? The cube root of, let me write negative 64. I already talked about that if we're talking the square root, it's fairly typical that, hey, you put a negative number in there, at least until we learn about imaginary numbers. We don't know what to do with it. But can we do something with this? Well, if I cube something, can I get a negative number?
I guess.
Sure.
Yeah, sure.
If I say this is equal to x, this is the same thing as saying that negative 64 is equal to x to the third power. Well, what could x be? Well, what happens if you take negative 4 times negative 4 times negative 4? Negative 4 times negative 4 is positive 16, but then times negative 4 is negative 64, is equal to negative 64. So what could x be here? Well, x could be equal to negative 4. X could be equal to negative 4. So based on the math that we know so far, you actually can take the cube root of a negative number. And just so you know, you don't have to stop there. You could take a fourth root. In this case, you'd have a 4 here, a fifth root, a sixth root, a seventh root of numbers. And we'll talk about that later in your mathematical career. But most of what you're going to see is actually going to be square root, and every now and then you're going to see a cube root. Now you might be saying, well, hey, look, you just knew that 3 to the third power is 27. You took the cube root, you get x. Is there any simple way to do this? And if I give you an arbitrary number, if I were to just say, I don't know, if I were to say cube root of 125. And the simple answer is, well, the easiest way to actually figure this out is actually just to do a factorization, in particular a prime factorization of this thing right over here, and then you would figure it out. So you would say, okay, well, 125 is 5 times 25, which is 5 times 5. All right, so this is the same thing as the cube root of 5 to the third power, which of course is going to be equal to 5. If you have a much larger number here, yes, there's no very simple way to compute what a cube root or a fourth root or a fifth root might be. And even square root can get quite difficult. There's no very simple way to just calculate it the way that you might multiply things or divide it.
That's true.
Let's see if we can find the cube root of 3,430. And if you're like me, it doesn't jump out of your mind what number times that same number times that same number, if you have 3 of those numbers and you were to multiply them together, would be equal to 3,430. So what I'm going to do is to try to prime factorize this, to find all the prime factors of 3,430 and see if any of those prime factors show up at least 3 times, and that'll help us with this. So 3,430, it's clearly divisible by 5 and 2, or it's divisible by 10. So let's do that. So first we can divide it by 2. It's 2 times, let's see, 3,430 divided by 2 is 1,715. Then we can divide it by 5 as well. We can factor 1,715 into 5 and, let me do a little bit of long division on the side here. So if I have 1,715, and I'm going to divide it by 5. 5 doesn't go into 1. It goes into 17 3 times. 3 times 5 is 15. Subtract. you get 2, and then you bring down a 1. 5 goes into 21 4 times. 4 times 5 is 20. Subtract, bring down the 5. 5 goes into 15 3 times, so it goes exactly 343 times. So 1,715 can be factored into 5 times 343. Now 343 might not jump out at you as a number that is easy to factor. It's clearly an odd number, so it won't be divisible by 2.
It's not divisible by 3
digits
as well.
add up to 10, which is not divisible by 3, so this isn't going to be divisible by 3. It's not going to be divisible by 4 because it's not divisible by 2. It's not going to be divisible by 5. If it wasn't divisible by 3 or 2, it's not going to be divisible by 6. And now we get to 7. 7, usually when you see kind of a nutty number like this that doesn't seem to be divisible by a lot of things, it's always a good idea to try things like 7, 11, 13, because those tend to construct very interesting numbers. So let's see if this is divisible by 7. So if I take 343, and if I want to divide it by 7, 7 goes into 30, doesn't go into 3, 7 goes into 34 4 times. 4 times 7 is 28. Subtract, 34 minus 28 is 6. Bring down a 3. 7 goes into 63 9 times. 9 times 7 is 63. Subtract, we don't have any remainder. And I forgot to do that last step up here. 3 times 15 is 15. Subtract, no remainder. Went in exactly. So here, 343 can be factored into 7 and 49.
Wow, 49, 7 times 7.
And 49, and 49 might jump out at you. It can be factored into 7 times 7. So this is interesting. I can rewrite all of this here, the cube root of 3,430 now, as the cube root of
10.
I'm just going to write it in its factored form. 2 times 5 times, I could write 7 times 7 times 7, or I could write times 7 to the third power. Times 7 to the third power. That captures these 3 7s right over here. I have 3 7s, and then I'm multiplying them together. So that's 7 to the third power. And from our exponent properties, we know that this is the exact same thing. This is the exact same thing as the cube root of 2 times 5 times the cube root. So let me do that in that same, just so we see what colors we're dealing with. So the cube root of 2 times 5, which is the cube root of 10, times the cube root, and I think you see where this is going, cube root of 7 to the third power. 7 to the third power. Keeping track of the colors is the hard part. 7 to the third power. And the cube root of 10, we just leave it as 10. We know the prime factorization of 10 is 2 times 5, so you're not going to just get a very simple integer answer here. You would get some decimal answer here. But here you get a very clear integer answer. The cube root of 7 to the third, well, that's just going to be 7. So this is just going to be 7. So our entire thing simplifies. This is equal to 7 times the cube root of 10. And this is about as simplified as we can get just using hand arithmetic. If you want to get the exact number here, you're probably best off using a calculator.
We're asked to find the cube root of negative 343. Or another way to think about it is some number that when I multiply it by itself 3 times, I'm going to get negative 343. Or another way to view it, this is the same thing as negative 343 to the 1/3 power. And the best way to do this is to really just try to factor this out. So the first thing we could do, so let me just factor negative 343. So the first thing I'd like to do is just factor out the negative 1. So this is the same thing as negative 1 times 343. And let's think about this. Is this divisible by 2? No. Is it divisible by 3? See, the digits do not add up to a multiple of 3. They add up to 10, so it's not divisible by 3. Not divisible by 4, since it's odd. Not divisible by 5, because it doesn't end with a 5 or 0. If it's not divisible by 6, because it's not divisible by 2 or 3. Is it divisible by 7? Let's check this out. So 7 goes into 343. 7 goes into 34 4 times. 4 times 7 is 28. 34 minus 28 is going to be 6. Bring down the 3. 7 goes into 63 exactly 9 times. And then we end up, so 9 times 7 is 63. No remainder. So this is going to be 7 times 49. And we know that 49 is the same thing as 7 times 7. So how can we rewrite this? This is the same thing as taking the cube root of -1 times 7 times 7 times 7, which is the same thing as taking the cube root of -1 times the cube root of 7 times 7 times 7. Now what's the cube root of -1? Well, -1 times itself 3 times is -1. So this right here is -1. You can verify -1 times -1 times -1 is indeed -1. This becomes +1, multiply by -1 again, you get -1. So this is -1. And then this over here, the cube root of 7 times 7 times 7, well, that's just going to be 7. 7 multiplied by itself 3 times gives us 7 times 7 times 7, or 343. So it's going to be -1 times 7, which is the same thing as -7. So our answer is -7. And we're done. We are asked to find the cube root of -512. Or another way to think about it is if I have some number and it is equal to the cube root of -512.
Just a sec. Right, call him back.
12. We are asked to find the cube root of -512. Or another way to think about it is if I have some number and it is equal to the cube root of -512.
Oh,
this just means that if I take that number and I raise it to the third power, then I get -512. And if it doesn't jump out at you immediately, what this is the cube of, or what we have to raise to the third power to get -512, the best thing to do is to just do a prime factorization of it. And before we do a prime factorization of it and to see which of these factors show up at least 3 times, let's at least think about the negative part a little bit. So -512, that's the same thing. So let me rewrite the expression. This is the same thing as the cube root of -1 times 512, which is the same thing as the cube root, of -1 times the cube root of 512. And this one's pretty straightforward to answer. What number, when I raise it to the third power, do I get -1? Well, I get -1. This right here is -1. -1 to the third power is equal to -1 times -1 times -1, which is equal to -1. So the cube root of -1 is -1. So it becomes -1 times this business right here, times the cube root of 512. And let's think what this might be. So let's do the prime factorization. So 512 is 2 times 256. 256 is 2 times 128. 128 is 2 times 64.
Why can't we do that kind of logic with square root? Square root -4. Oh, I guess you can square -1.
I already see a 2 3 times. 64 is 2 times 32. 32 is 2 times 16. We're getting a lot of 2's here. 16 is 2 times 8. 8 is 2 times 4, and 4 is 2 times 2. So we got a lot of 2's if you multiply. So essentially, if you multiply 2, 1, 2, 3, 4, 5, 6, 7, 8, 9 times, you're going to get 512, or 2 to the 9th power is 512. And that by itself
1, 2, 3, 4, 5, 6, 7, 8
should give you a clue of what the cube root is. But 2 to the 9th power is 512. 9, essentially, if you multiply 2, 1, 2,
You're wrong, man. 1, 2, 3, 4, 5, 6, 7, 8.
3, 4, 5, 6, 7. If you multiply, so essentially if you multiply 2, 1, 2, 3, 4, 5, 6, 7, 8, 9 times.
Wait. Let's get 1,000, right? Holy shit, what? No, you said multiply to 9 times, so you get 10 twos, right? Oh my god.
You're going to get 512.
Oh, that's actually wrong.
2 to the 9, 500. $512. Twos. We got a lot of twos if you multiply. So essentially, if you multiply 2, 1, 2, 3, 4, 5, 6, 7, 8, 9 times, you're going to get 5.
Multiply to by itself.
The ninth power is 512. And that by itself...
It's confusing. I mean, if you multiply 2 by itself 2 times, then that would be like 2 to the third. So, if you multiply 2 by itself 1 time, then that's just 2 raised to 0. If you multiply 2 by itself, no, actually 1 time, 2 times, 9 times. Wait, what? No, this is raised. If you multiply by itself 1 time, 2 times, then it's gonna be 2 times 2 times 2. Or that's 2 raised. Yeah, correct.
itself should give you a clue of what the cube root is. But another way to think about it is, so essentially if you multiply 2, 1, 2, 3, 4, 5, 6, 7, 8, 9 times, you're going to get 1, 2, 3 times 2. So we got a lot of 2's if you multiply. So essentially if you multiply 2, 1, 2, 3, 4, 5, 6, 7, 8, 9 times, you're going to get 512, or 2 to the 9th. Can we find, there's definitely 3 2's here, but can we find 3 groups of 2's, or can we, if we could also find, let me look at it this way, we can find 3 groups of 2 2's over here. So that's 2 times 2 is 4, 2 times 2 is 4, so definitely 4 multiplied by itself 3 times is divisible into this. But even better, it looks like we can get 3 groups of 3 2's. So 1 group, 2 groups, and 3 groups.
Get 8 outside.
So each of these groups, 2 times 2 times 2, that's 8. That is 8. This is 2 times 2 times 2, that's 8. And this is also 2 times 2 times 2, so that's 8. So we could write 512 as being equal to 8 times 8 times 8. And so we can rewrite this expression right over here as the cube root of 8 times 8 times 8. So this is equal to,
holy shit,
this is equal to -1, or I could just put a negative sign here. -1 times the cube root the cube root of 8 times 8 times 8. So we're asking our question, what number can we multiply by itself 3 times, or to the third power, to get 512, which is the same thing as 8 times 8 times 8? Well, clearly, this is 8. So the answer, this part right over here, is just going to simplify to 8. And so our answer to this, the cube root of negative 512, is negative 8. And we are done. And you could verify this. Multiply negative 8 times itself 3 times. Well, let's just do it. Negative 8 times negative 8 times negative 8. Negative 8 times negative 8 is positive 64. You multiply that times negative 8, you get negative 512.
Okay, so I kind of posted this. It's a mistake thing. I do think it's a mistake though. Could be wrong, so let's see who's gonna comment on this.
To find the cube root.
Okay. The cube root of a number is a factor we multiply itself 3 times to get that number. The symbol for cube root is check with 3 on it. Finding the cube root is the opposite of giving a number. Yep. Oh, wow, this is hard. Oh no, I don't know. 36 times 6. Oh my god, it's gonna be 100? No, it's just 10. Oh wow, quiz already. Let's do the cube root activities first. Damn, that's insane. If it's 8, it's 512. Let's do 9. 81 times 9. Whoa, okay. 72. Okay, cool. I've read this one. This one's like 7 right now. It's 5. Holy cow, that's insane. Let's try 11. I'm pretty sure it's 11. Wait, what? This is 8, right? 4. Oh man, it's insane. Let's try 12. It's gonna be 4 2 0 2 1 4 4 1 4. 4 times 12 is gonna be 14. Yeah, I got 8 already. 2, and then we got 0, we got 4. Okay, it's gonna be 12. Start quiz. Let's go for the quiz. Oh wow. Oh shit, no, it's not 5. Square root of 125. Holy shit. Can I do a calculator? Remove all perfect squares. Okay, let's actually prime factorize this. This is 525. You have 5 times 5, so we have 5 and square root of 5, I believe. Let's try again for last time. It's 5 times 5. Okay, that's correct. Oh wow, it's 10. Find the square root at 6. 6 times 6 is 36. Least to greatest. Okay, cool. 9 times 9 is 81. 8 times 8 is 64. Oh wow, this is hard. This is 8. 8 times 8 is 64, right? Square root. Okay. Nice. Let's do exponents.
In this video, I want to do a bunch of examples involving exponent properties, but before I even do that, let's have a little bit of a review of what an exponent even is. So let's say I had 2 to the third power. You might be tempted to say, oh, is that 6? And I would say, no, it is not 6. This means 2 times itself 3 times. So this is going to be equal to 2 times 2 times 2, which is equal to 2 times 2 is 4. 4 times 2 is equal to 8. If I were to ask you what 3 to the second power is, or 3 squared, this is equal to 3 times itself 2 times. This is equal to 3 times 3, which is equal to 9.
No, that's just one time, dude.
Let's do one more of these. I think you're getting the general sense if you've never seen these before. Let's say I have, I don't know, 5 to the 7th power. That's equal to 5 times itself 7 times. 5 times 5 times 5 times 5 times 5 times 5 times 5. That's 7, right? 1, 2, 3, 4, 5, 6, 7. And this is going to be a really large number. And I'm not going to calculate it right now. If you want to do it by hand, feel free to do so, or use a calculator. But this is a really in this
The part at 13, 10. It's not even. Oh shit, actually.
Really large number. So one thing that you might appreciate very quickly is that exponents increase very rapidly. 5 to the 17th would be even a way more massive number. But anyway, that's a review of exponents. Let's get a little.
My voice. Okay, cool.
Let's get a little bit steeped in algebra using exponents. So what would 3x, let me do this in a different color. What would 3x times 3x times 3x be? Well, one thing you need to remember about multiplication is it doesn't matter what order you do the multiplication in. So this is going to be the same thing as 3 times 3 times 3 times x times x times x. And just based on what we reviewed just here, that part right there, 3 times 3 3 times, that's 3 to the third power. And this right here, x times itself 3 times, that's x to the third power. So this whole thing can be written as 3 to the third times x to the third. Or if you know what 3 to the third is, this is 9 times 3, which is 27. This is 27 x to the third power. Now you might have said, hey, well, wasn't 3x times 3x times 3x? Well, 3x, let me do this. It's a review of exponents. Let's get a little, what would 3x, let me do this in a different color. What would 3x times 3x, right there, this to right here, x times this, if you know 7, x times 3x, what power? Now you might have said, hey, well, wasn't 3x times 3x times 3x, wasn't that 3x to the third power, right? You're multiplying 3x times itself 3 times. And I would say, yes, it is. So this right here you could interpret that as 3x to the third power. And just like that, we stumbled on one of our exponent properties. Notice this. When I have something times something, and that whole thing is to the third power, that equals each of those things to the third power times each other. So 3x to the third is the same thing as 3 to the third times x to the third times x to the third, which is 27 to the third power. Let's do a couple more examples. What if I were to ask you what 6 to the third times 6 to the sixth power is? And this is going to be a really huge number, but I want to write it as a power of 6. And let me write the 6 to the 6 actually in a different color. 6 to the 6 times 6 to the third times 6 to the sixth power. What is this going to be equal to?
6 to the ninth power.
Well, 6 to the third, we know that
9.
6 times itself 3 times. So it's 6 times 6 times 6. And then that's going to be times, times here is in green, so I'll do it in green. Or maybe I'll make both of them in orange. That is going to be times 6 to the sixth power. Well, what's 6 to the sixth power? That's 6 times itself 6 times. So it's 6 times 6 times 6 times 6 times 6. Let's see, that's 5. Then you get one more times 6. So what is this whole number going to be? Well, this whole thing, we're multiplying 6 times itself how many times? 1, 2, 3, 4, 5, 6, 7, 8, 9 times, right? 3 times here, and then another 6 times here. So we're multiplying 6 times itself 9 times. 3 plus 6. So this is equal to 6 to the 3 plus 6th power, or 6 to the 9th power. And just like that, we've stumbled on another exponent property. When we take exponents, in this case, 6 to the third, the number 6 is the base. We're taking the base to the exponent of 3. When you have the same base, and you're multiplying two exponents with the same base, you can add the exponents. So if I have,
what's the
let
different
me do
base?
several more examples of this. If I have, let's do it in magenta. Let's say I had 2 squared times 2 to the 4th times 2 to the 6th. Well, I have the same base in all of these, so I can add the exponents. This is going to be equal to 2 to the 2 plus 4 plus 6, which is equal to 2 to the 12th power. And hopefully that makes sense, because this is going to be 2 times 2 times itself 2 times, 2 times itself 4 times, 2 times itself 6 times. So when you multiply them all out, it's going to be 2 times itself 12 times, or 2 to the 12th power. Let's do it in with a little bit more abstract way, using some variables, but it's the same exact idea. What is x to the squared, or x squared times x to the 4th? Well, we could use the property we just learned. We have the exact same base, x. So it's going to be x to the 2 plus 4 power. It's going to be x to the 6th power. And if you don't believe me, what is x squared? X squared is equal to x times x. And if you're going to multiply that times x to the 4th, you're multiplying it by x times itself 4 times. X times x times x times x. So how many times are you now multiplying x by itself? Well, 1, 2, 3, 4, 5, 6 times. X to the 6th power. Let's do another one of these. The more examples you see, I figure the better. So let me do the other property just to mix and match it. Let's say I have a to the third to the 4th power. So I'll tell you the property here, and then I'll show you why it makes sense. When you have something to an exponent, and then you raise that to an exponent, you can multiply the exponents. So this is going to be a to the 3 times 4 power, or a to the 12th power. And why does that make sense? Well, this right here is a to the third times itself 4 times. So this is equal to a to the third times a to the third times a to the third times a to the third. Well, we have the same base, so we can add the exponents. So this is going to be a to the 3 times 4, right? This is equal to a to the 3 plus 3 plus 3 plus 3 power, which is the same thing as a to the 3 times 4 power, or a to the 12th power. So just to review the properties we've learned so far in this video, besides just a review of what an exponent is, if I have something, let's say I have x to the a power times x to the b power, this is going to be equal to x to the a plus b power. We saw that right here. We saw that right here. X squared times x to the 4th is equal to x to the 6th, 2 plus 4. We also saw that if I have x times y to the a power, this is the same thing as x to the a power times y to the a power. We saw that early on in this video. We saw that over here. 3x to the 3rd is the same thing as 3 to the 3rd times x to the 3rd. That's what this is saying right here. 3x to the 3rd is the same thing as 3 to the 3rd times x to the 3rd. And then the last property, which we just stumbled upon, is if you have x to the a, and then you raise that to the bth power, that's equal to x to the a times b. And we saw that right there. A to the 3rd, and then raise that to the 4th power, is the same thing as a to the 3 times 4, or a to the 12th power. So let's use the properties, these properties, to do a handful of what we could call more complex problems. So let's say we had, I don't know, let's say I want to do something a little bit. Let's say we have 2xy squared times negative x squared y squared times 3x squared y squared. And we wanted to simplify this. Well, a good place to start, let's see, maybe we could simplify this. This you could view as negative 1 times x squared times y squared. So just this part right here, if we take this whole thing to the squared power, this is like raising each of these to the 2nd power. So this part right here could be simplified as negative 1 squared times x squared squared times y squared. And then if we were to simplify that, negative 1 squared is just 1. X squared squared. Remember, you can just multiply the exponents. So that's going to be x to the 4th y squared. That's what this middle part simplifies to. And let's see if we can merge it with the other parts. The other parts, just to remember, were 2xy squared and then 3x squared y squared. Well, now we're just going ahead and just straight up multiplying everything, and we learned in multiplication that it doesn't matter which order you multiply things in. So I can just rearrange. We're just going and multiplying 2 times x times y squared times x to the 4th times y squared times 3 times x squared times y squared. So I can rearrange this, and I will rearrange it so that it's in a way that it's easy to simplify. So I can multiply 2 times 3, and then I can worry about the x terms. Let me do it in this color. Then I have times x times x to the 4th times x squared times x squared. And then I have to worry about the y terms. Times y squared times y squared times another y squared times another y squared times another y squared. And now what are these equal to? Well, 2 times 3, you knew how to do that. That's equal to 6. And what is x times x to the 4th times x squared? Well, one thing to remember is x is the same thing as x to the 1st power. Anything to the 1st power is just that number. So, 2 to the 1st power is just 2. 3 to the 1st power is just 3. So what is this going to be equal to? This is going to be equal to, we can add, we have the same base, x, we can add the exponents. X to the 1 plus 4 plus 2 power, and I will add it in the next step. And then on the y's, this is times y to the 2 plus 2 plus 2 power. And what does that give us? That gives us 6 x to the 7th power, y to the 6th power. Now I'll just leave you with something that you might already know, but it's pretty interesting, and that's the question of what happens when you take something to the 0th power. So if I say 7 to the 0th power, what does that equal? And I'll tell you right now, this might seem very counterintuitive, this is equal to 1. Or 1 to the 0th power is also equal to 1. anything to the 0th power, any non-zero number to the 0th power is going to be equal to 1. And just to give you a little bit of an intuition on why that is, think about it this way. Think about it this way. 3 to the first power, so let me write the powers. 3 to the first, second, third, we'll just do it with the number 3. With the number 3. So 3 to the first power is 3, I think that makes sense. 3 to the second power is 9. 3 to the third power is 27. And of course, we're trying to figure out what should 3 to the 0th power be. Well, think about it. Every time you decrement the exponent, every time you take the exponent down by 1, you are dividing by 3. To go from 27 to 9, you divide by 3. To go from 9 to 3, you divide by 3. So to go from this exponent to that exponent, maybe we should divide by 3 again. And that's why anything to the 0th power, in this case 3 to the 0th power, is 1. See you in the next video. 1 to the 0th power is also equal to 1. Anything to the 0th power, any non-zero number to the 0th power, is going to be equal to 1. And just to give you a little bit of an intuition on why that is, think about it this way. Think about it this way. 3 to the first power, so let me write the powers.
Oh my god, it's a lot of questions. Let's do this.
I now want to go over some of the other core exponent properties, but they really just fall out of what we already know about exponents. Let's say I have two numbers, a and b, and I'm going to raise it to, I could do it in the abstract, I could raise it to the c power, but I'll do it a little bit more concrete. Let's raise it to the 4th power. What is that going to be equal to? Well, that's going to be equal to, I could write it like this. Let me copy and paste this. Copy and paste. That's going to be equal to AB times AB times AB times AB times AB. But what is that equal to? Well, when you just multiply a bunch of numbers like this, it doesn't matter what order you're going to multiply it in. So you could, this right over here is going to be equivalent to A times A times A times A times, we have 4 b's as well that we're multiplying together, times b times b times b times b. And what is that equal to? Well, this right over here is a to the 4th power, and this right over here is b to the 4th power, And so you see, if you take the product of two numbers and you raise them to some exponent, that's equivalent to taking each of the numbers to that exponent and then taking their product. And here I just used the example with 4, but you could do this really with any arbitrary, you could do this with actually any integer, or actually any exponent. You can actually, this property holds. And you could satisfy yourself by trying different values and using the same logic right over here. But this is a general property that, let me write it this way, that if I have a to the b to the c power, that this is going to be equal to a to the c times b to the c times b to the c times b to the c power. And we'll use this throughout actually mathematics when we try to simplify things or rewrite an expression in a different way. Now let me introduce you another core idea here. And this is the idea of raising something to some power, and I'll just use the example of 3, and then raising that to some power. What could this be simplified as? Well, let's think about it. This is the same thing as a to the 3rd. This is the same thing. Let me copy and paste that. Is a to the 3rd times a to the 3rd. Is a to the 3rd times a to the 3rd. And what is a to the 3rd times? This is equal to a to the 3rd times a to the 3rd. And that's going to be equal to a to the 3 plus 3 power. We have the same base. And so we would add, and they're being multiplied. They're being raised to these two exponents. So it's going to be the sum of the exponents, which of course is going to be equal to a to the, that's a different color, a. It's going to be a to the 6th power. A to the 6th power. So what just happened over here? Well, I took two 8 to the thirds and I multiplied them together. So I took these two 3's and added them together. So this essentially right over here, you could view this as 2 times 3. This right over here is 2 times 3. That's how we got the 6. When I raised something to one exponent and then raised it to another, that's equivalent to raising the base to the product of those two exponents. I just did it with this example right over here. But I encourage you, try other numbers to see how this works. And I could do this in general. I could say a to the b power, and then let me copy and paste that. So copy, and then I'm going to raise that, and I'm going to raise that to the c power. I'm going to raise that to the c power. Well, what is that going to give me? Well, I'm essentially going to have to take c of these. So 1, 2, 3. I don't know how large of a number c is, so I'll just do dot, dot, dot. So dot, dot, dot. I have c of these right over here. So that's what, so I have c of these. So there's c of them right over there. So what is that going to be equal to? Well, that is going to be equal to a to the, well, for each of these c, I'm going to have a b that I'm going to add together. So let me write this. So I'm going to have a b plus b plus b plus dot, dot, dot plus b. And now I have c of these b's. So I have c b's right over here. Or you could view this as a, this is equal to a to the c times b power. C, or a, you could view a to the cb power. So very useful. So if someone were to say, what is 35 to the third power, and then that raised to the 7th power, well, this is obviously going to be a huge number, but we can at least simplify the expression. This is going to be equal to 35 to the product of these two exponents. It's going to be 35 to the 3 times 7, or 35 to the 21, or to the 21st power.
Wow.
Let's do some exponent examples that involve division. Let's say I were to ask you what 5 to the 6th power divided by 5 to the 2nd power is. Well, we could just go to the basic definition of what an exponent represents and say, well, 5 to the 6th power, that's going to be 5 times 5 times 5 times 5 times 5, one more 5, times 5. 5 times itself 6 times. And 5 squared, that's just 5 times itself 2 times. So it's going to be 5 times 5. Well, we know how to simplify a fraction or a rational expression like this. We can divide the numerator and the denominator by 1 5, and then these will cancel out. And then we can do it by another 5, or this 5 and this 5 will cancel out. And what are we going to be left with? 5 times 5 times 5 times 5 over, well, you could say over 1, or you could say that this is just 5 to the 4th power. Now notice what happens. Essentially, we started with 6 in the numerator, 6 5s multiplied by themselves in the numerator, and then we subtracted out. We were able to cancel out the 2 in the denominator. So this really was equal to 5 to the 6th power minus 2. So we were able to subtract the exponent in the denominator from the exponent in the numerator. And let's remember how this relates to multiplication. If I had 5 to the, let me do this in different colors, 5 to the 6th times 5 to the 2nd power, we saw in the last video that this is equal to 5 to the 6 plus, I'm trying to make it color-coded for you, 6 plus 2 power. Now we see a new property, and in the next video we're going to see that these aren't really different properties, that they're kind of same sides of the same coin when we learn about negative exponents. But now in this video, we same sides of the same coin when we learn about negative exponents. But now in this video, we just saw that 5 to the 6th power divided by 5 to the 2nd power, 5 to the, let me do it in a different color, 5 to the second power is going to be equal to 5 to the, it's time consuming to make it color coded for you, 6 minus 2 power. 6 minus 2 power, or 5 to the fourth power. Here it's going to be 5 to the eighth. So when you multiply exponents with the same base, you add the exponents. When you divide with the same base, you subtract the numerator exponent. You subtract the denominator exponent from the numerator exponent. Let's do a bunch more of these examples right here. Let's do a bunch more. What is 6 to the seventh power divided by 6 to the third power? Well, once again, we can just use this property. This is going to be 6 to the 7 minus 3 power, which is equal to 6 to the fourth power. And you could multiply it out this way, like we did in the first problem, and verify that it indeed will be 6 to the fourth power. Now let's try something interesting. Let's try something interesting, and this will be a good segue into the next video. Let's say we have 3 to the fourth power divided by 3 to the 10th power. Well, if we just go from basic principles, this would be 3 times 3 times 3 times 3, all of that over 3 times 3. We're going to have 10 of these. 3 times 3 times 3 times 3 times 3 times 3. How many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, if we do what we did in the last video, this 3 cancels with that 3, those 3's cancel, those 3's cancel, those 3's cancel, and we're left with 1 over 1, 2, 3, 4, 5, 6 3's. So 1 over 3 to the sixth power, right? We have 1 over all of these 3's down here. But that property that I just told you would have told you that, look, this should also be equal to 3 to the 4 minus 10 power. Well, what's 4 minus 10? We're going to get a negative number. This is 3 to the negative 6th power. So using the property we just saw, you'd get 3 to the negative 6th power. Just multiplying them out, you get 1 over 3 to the 6th power. And the fun part about all of this is these are the same quantity. So now you're learning a little bit about what it means to take a negative exponent. 3 to the negative 6th power is equal to 1 over 3 to the 6th power. And I'm going to do many, many more examples of this in the next video. But if you take anything to the negative power, so a to the negative b power is equal to 1 over a to the b. That's one thing that we just established just now. And earlier in this video, we saw that if I have a to the b over a to the c, that this is equal to a to the b minus c. That's the other property we've been using. Now, using what we've just learned and what we learned in the last video, let's do some more complicated problems. Let's do some more complicated problems. Let's say I have a to the third, b to the fourth power over a squared b, and all of that to the third power. Well, we can use the property we just learned to simplify the inside. This is going to be equal to a to the third divided by a squared. That's a to the 3 minus 2 power, right? So this would simplify to just an a. And you can imagine this is a times a times a divided by a times a. You'll just have an a on top. And then the b to the fourth divided by b, well, that's just going to be b to the third. Right? This is b to the first power. 4 minus 1 is 3. And then all of that in parentheses to the third power. I don't want to forget about this third power out here. This third power is this one. Let me color code it. That third power is that one right there. And then this a in orange is that a right there. And I think we understand what maps to what. And now we can use the property that when you multiply something and take it to the third power, that's equivalent of taking each of these. This is equal to a to the third power times b to the third power. And then this is going to be equal to, a to the third power. I'll do it like this. A to the third power. That's just a to the third right there. And then what is this? Times b to the 3 times 3 power, times b to the 9th. And we would have simplified this about as far as you can go. Let's do one more of these. Power is equal to a to the third power times b to the third to the
Why did you
third
have to do
power.
the parenthesis?
And then this is going to be equal to, this is equal to a to the third power.
Okay, I get it.
I'll do it like this. A to the third power. That's just a to the third right there. And then what is this? Times b to the 3 times 3 power, times b to the 9th. And we would have simplified this about as far as you can go. Let's do one more of these, because I think they're good practice and super valuable experience, I think, later on. Let's say I have 25 x y to the 6th over 20 y to the 5th y to the 5th x squared. So once again, we can rearrange the numerators and the denominators. So this you could rewrite as 25 over 20 times x over x squared.
You know what? I want to try this one. I'm gonna grab my pen and that looks it. Okay, I'm back. We have 5 for x 6. So we have just y at top. Yo, how do I do the 5 to 4x squared one? So I guess it's the same thing as uh 5 raised to 1y.
Right? We could have made this bottom 20 x squared y to the 5th. It doesn't matter the order we do it in. Times y to the 6th over y to the 5th. And let's use our newly learned exponent properties and actually just simplifying fractions. 25 over 20, if you divide them both by 5, you're going to get, this is equal to 5 over 4. X divided by x squared, well, there's two ways you could think about it. That you could view as x to the negative 1. You know, you have a first power here. 1 minus 2 is negative 1. So this right here is equal to x to the negative 1 power, or it could also be equal to 1 over x. These are equivalent. So let's say that this is equivalent to 1 over x, just like that. And it would be x over x times x. One of those sets of x's would cancel out, and you're just left with 1 over x. And then finally, y to the 6th over y to the 5th, that's y. That right there is y to the 6th minus 5 power, which is just y to the first power, or just y. So times y. So if you want to write it all out as just one combined rational expression, you have 5 times 1 times y, which would be 5y. All of that over 4 times x. Right? This is y over 1, so 4 times x times 1. All of that over 4x. And we have successfully simplified it.
That's cool. Extremely cool, man.
Let's do some exponent. Let's do over a to the c, that this is equal to a to the b minus c. That's the
What's so funny about that? Oh wow, it's a lot of properties. You're not touching the base. Okay. But isn't that supposed to help some kind of... Wow, okay. Yo, what the fuck? Oh. Product of power per product, power by power. Just one? Okay. How about the 4 though? I think it's 4 raised to 2 times x raised to 2, right? Or let's say 4 times 16. 16 x. This is right. Say the equivalent expression. Okay, it's gonna be y to the 6. Okay. 6, 9. To 25. What if I say you 5 raised to 2? You gonna accept that? Yo, what the fuck? Okay. What is that? Okay. Select the equation, the equivalent expression. Okay. A raised to 4, then times 12. Okay. Oh yeah. Let's not take the quiz. Let's do the exercises first. God damn. Alright, the expression. 5 raised to 7. B raised to 5. Solve for x. Oh. Powers of powers. Seven raised to 9. Wait, am I supposed to, I'm not supposed to multiply the base, right? But earlier I kind of did. Not really. Four raised to 5. Yep. Solve for x. 1. Y raised to 7. Oh wow. 5 is 2 minus 4. 4. Okay. Powers of products and quotients. Structured practice. Okay. 6, 6. 4x. 16x squared, I believe. Select the equivalent expression. No, this one works. No. Okay. Write the expression in the following. Okay, 8 times y raised to 12. Powers of products and quotients. Select the equivalent expression. Okay, it's gonna be y raised to 6. This one's the only one raised to 6. And then 2, 10. Yeah, that makes sense. Choose the 3 expressions that are equivalent to 9. Alright, 3 expressions, okay. 9 times 9 times 9. This one's 9 to the 4th. What is this? This is 9 to the 2nd power. Times 2, okay. Say the experience expression 10 to the 10th power and 7 to the 25. Set expression 8 to 6. This one 6 and 4 to 12. Okay, this one. Okay, let's do the quiz. Write the expression in the form 5 to the nth power. Okay, whatever. 5 raised to 6. It's 5 raised to 7. Select the equivalent. Why didn't I have any questions related to cube roots and stuff like that? Select the equivalent expression 7 halves over 8. Wait, what? Oh, this one. Select the equivalent expression a to the 4th and then b to the 12th. Make sense? X raised to 8. And we're done. Okay. Oh, actually the take. I don't even remember. Wow. Let's see. So I only have wow, negative exponents. Quiz 4, quiz 5, and then unit test. Okay, it's gonna be for tomorrow. Right now, this is it. Let's see our stuffs. 51% to like almost done. I'm almost done. Wow, and then the course challenge. It's gonna be insane. 96. I don't know what these things are. Great Listener exponents. What? Okay, 27%. Okay. I guess this is part 22, I believe. Okay. We'll continue tomorrow. Bye.